ठीक है, और किसको समझ में? आई वांट टू सी हैंड्स इफ एनीबॉडी हैज अंडरस्टूड एट ऑल. Azeotrope and minimum boiling azeotrope and maximum boiling azeotrope. Nobody has understood. I don't see any hands. Only one person. That's very bad here. That reflects very badly on me. And I could not explain it to you. Okay. So Devendra explain what is an azeotrope. Azeotrope समझ में आया लोगों को? Do you understand what is an azeotrope? How many people understand azeotrope? I want to see raise hand. Raise hand if you understand azeotrope. Okay. So about 8 to 10 people understand azeotrope. Rest of them don't understand. Okay. So azeotrope is essentially when we do vapor liquid equilibrium, when we boil a liquid, minimum 2 components, the vapor has more of लोअर बॉइलिंग कंपोनेंट. जिसका बॉइलिंग पॉइंट कम रहता है उसका वेपर में कंपोजिशन ज़्यादा रहता है लिक्विड से जनरली. दैट इज VLE. अगर VLE नहीं समझा तो देन यू आर इन द रॉन्ग प्लेस. देन यू आर हियर ओनली फॉर अटेंडेंस. ओके. एंड देन आई डोंट इवन रियली केयर अबाउट यू इफ यू डोंट अंडरस्टैंड VLE. ओके. तो आपको अटेंडेंस मिल रहा है लेकिन समझने की कोशिश नहीं कर रहे हैं. 8-10 लोग हैं जो समझने की कोशिश कर रहे हैं, जिनको समझ में आ रहा है. तो VLE में normally the vapor composition is more than the liquid composition for the lower boiling component. जो more volatile रहता है उसका composition vapor में ज़्यादा रहता है. And that is the principle which is used in distillation, because if I take the vapor which is in equilibrium with the liquid and condense it, I have shown that example before. If I take, say, this example, and if I take composition X, this is X and this is Y. If I take liquid with more volatile component with composition 0.3, I'll get a vapor which has more volatile component is 0.7. That means it is richer in more volatile component. So if I take this liquid, vaporize it and condense this vapor, I'll get a solution which is having more of lower boiling component or more volatile component, and that is the principle of separation used in distillation. But what happens in azeotrope? When I boil it, the vapor will have the same composition as the liquid. तो कोई फायदा नहीं है, डिस्टिलेशन कर नहीं सकते, सेपरेशन कर नहीं सकते. जितना लिक्विड कंपोजिशन रहेगा उतना ही वेपर कंपोजिशन रहेगा, राइट? एंड दैट हैपेंस बिकॉज ऑफ नॉन आइडियलिटी, because of positive deviations from ideality and negative deviations from ideality. What is positive deviation from ideality? Can anybody explain? What do you mean by positive deviations from ideality? Has anybody understood what is positive deviations from ideality and negative deviations from ideality? I want to raise hands. Raise hands if you understood. Okay, so tell me what is positive deviations from ideality if you understood it. Anybody can tell me. Only 5 people understood that. Cindy, can you tell what is positive deviations of ideality?
A real gas pressure is more than ideal gas.
What is it?
A real gas pressure.
आवाज कट रहा है आपका. ठीक है, प्रणव पवार, कैन यू एक्सप्लेन व्हाट इज पॉजिटिव डिविएशन ऑफ आइडियलिटी? प्रणव पवार.
Hello.
Yeah, can you
Yes.
tell what is ideal?
Yes.
Positive deviations of ideality?
Yes, sir. That actual pressure is greater than the pressure that we calculate by Raoult's law.
Yes, good. So partial pressure of any component in the vapor phase which is in equilibrium with the liquid is more than that given by Raoult's law. Raoult's law क्या है? You know Raoult's law, right? This is Raoult's law for ideal gases, for ideal solutions and ideal things, right? So partial pressure is equal to xi pis. But actual partial pressure, if we measure, if it is more than the value given by this equation, then it is positive deviations from ideal. ज़्यादा है तो positive है. And negative deviations means the partial pressure actual is less than the value given by this equation. Is this understood? How many people understand this now?
Yes, sir.
Raise hands. When I ask you raise hands, I want to see the hands now, because this is a topic which is not easy. So if you understand, at least raise the hands that you understand what is positive deviations and what is negative deviations. Okay, good. So if you understand this, when I look at, let me go back and show you that diagram again. Okay, so this was a system in which we are plotting the pressure, partial pressure versus x, and if you look at the y-axis, this is vapor pressure of pure component at x equal to 1 CS2, and this is the vapor pressure of pure component acetone at x equal to 1 for acetone, x equal to 0 for CS2, so it is 1 for acetone. So pure component vapor pressure दिया है, ये है अपना, and if you join 0 with this thing, you get a straight line which is essentially Raoult's law, which says that yi into P is equal to xi into PIS. Right? So partial pressure is this one. Right? So PI bar bolo, PI bolo, doesn't matter. So PI bar, partial pressure is equal to xi PI, that means a straight line, right? So if I plot it versus xi, I should get a straight line. And at xi equal to 1, it should become equal to PI. That's what is happening here. So this is following Raoult's law. But actual partial pressure, this is what is actual partial pressure, is more than the value given by Raoult's law. So if I take any value, any vertical line, if this value of x, value of Raoult given by Raoult's law is this one, value given by or found by experiment is this one. So experimental value is more than the value or calculations by Raoult's law. So that is positive deviations from ideality. Is this clear?
Yes, sir.
Okay. And to talk about negative deviations, it is ulta. So this is Raoult's law again. This is Raoult's law, and this is the real value, actual value. So actual value is, if I take this vertical line, this is the value given measured actually, and this is the value given by Raoult's law. So its actual value is less than the value given by Raoult's law. So it is negative deviations from ideality. Is this understood?
Yes, sir.
Okay. So if you understand this, now let us go to azeotrops. Azeotrops, and what you have seen is that what you call as x1 equal to y1 होता है, well, you'll see that. But if you plot pressure versus x1 for a positive deviations, for solutions with positive deviations from ideality, you'll get this type of curve, and it upper one is Px curve and the lower one is Py curve. And these intersect at this point, which is the azeotropic composition. So at this point, if I take a mixture, if there's a composition of liquid which is given by this one, this value, vapor will have the same composition. And at this point, x1 equal to y1. Which फर्क नहीं है because they are intersecting at that point. Whereas in these other curves, if I take any value, suppose I take this line, okay, this is x value, this is y value, okay, so it's a different thing, it's not the same thing, but at this value it is same. At this azeotropic composition, x is equal to y, right? So if I plot the same for the same system, if I plot temperature versus x, what I'll get is this is the temperature of component 1, which is more boiling component, a more volatile component, so it is less, and T2 is boiling point of component 2, which is less volatile component. And again, the curve will be inverse because pressure और temperature उल्टा रहता है, pressure बढ़ता है, temperature कम होता है. So what will happen is, in this case, the intersection will be here. The intersection will be here, which is again x equal to y, and the temperature is less than T1 and less than T2. The temperature at which this vapor will form, or this azeotrope will form, is less than the boiling point of component 1 and also less than the boiling point of component 2, and that is why it is called minimum boiling azeotrope. Is this understood? Why it is called minimum boiling azeotrope?
So repeat. सांग. सर फिर से बताओ ना एक बार.
Okay, so in this case we plot temperature versus x and y. What you'll get is a composition of azeotrope which boils at a temperature which is less than the boiling point of component 1 and the boiling point of component 2, both. दिख रहा है आपको temperature? This temperature is less than T1, is less than T2. Can you see this?
Yes, sir.
And that is why it is called minimum boiling azeotrope. Is this understood?
Yes, sir.
Yes, sir.
Yes, sir.
How many will understand this? I want to see hands. Okay, so significant number of people understand. Others, if they're not understanding, then there's some issue. Okay, so if I plot, that is positive deviation from ideality. So if I take the other system, which is negative deviation from ideality, you have seen the curve is concave. Pxy curve is like this. And in this case, this is the point, sorry, this is the point where the Px and Py curve intersect. That means at this point, again, x1 is equal to y1, same value. So it is an azeotrope, right? And if I plot again this for the same system, Txy curve, they will intersect at this point, and this temperature is more than T2 and is more than T1. So it is more, the temperature of the azeotrope at which it boils is more than the boiling point of component 1 and also more than the boiling point of component 2. And that is why it is called maximum boiling azeotrope. Is this understood?
Yes, sir.
Yes, sir.
So how many people understand this? Raise your hand. Okay, good. So if you understand this, so now let's go back to the same ऊपर वाला positive deviations from ideality वाला, and if we plot y-x curve or xy curve or equilibrium diagram, what we find is this type of curve, ये जो है,
सर
yes,
सर ये जो हम बॉइलिंग पॉइंट ले रहे हैं वो मैक्सिमम और मिनिमम वो मिक्सचर का होगा ना?
मिक्सचर का ही है.
हाँ तो सर वो मेरा कल का ही वही क्वेश्चन में डाउट था कि अगर दो लिक्विड ले रहे हैं उसका बॉइलिंग पॉइंट मिक्सचर का बॉइलिंग पॉइंट उन दोनों से मिक्सचर के कम होगा प्योर बॉइलिंग पॉइंट के से.
हाँ,
हाँ तो सर वो प्रैक्टिकलिटी में नेगेटिव होता है क्या? लेकिन
प्रैक्टिकली डेटा की बात कर रहा हूँ मैं. इज नॉट थ्योरी. We're not talking about theory now. We are just looking at data, experimental data, and explaining it. Why is it called minimum and maximum boiling as you drop?
नहीं सर मैं पूछ रहा हूँ सर वो नेगेटिव डेविएशन जो होता है उसमें वो बॉइलिंग पॉइंट मिक्सचर का दोनों प्योर के से ज्यादा आता है ना?
ज़्यादा भी आता है, कम भी आता है. It depends on the molecules. It depends on the interaction between the molecules. जैसे पॉजिटिव डिविएशन हम आइडियलिटी देखा था, पार्शियल प्रेशर इज मोर देन द आइडियल पार्शियल प्रेशर, राइट? दैट इज पॉजिटिव डिविएशन ऑफ आइडियलिटी. नेगेटिव डिविएशन बोला तो पार्शियल प्रेशर इज लेस देन दैट गिवन बाय आइडियल और आइडियल सॉल्यूशंस, right? That's what it translates into. If it is positive deviations, the temperature of that mixture of that azeotrope is going to be less than the temperature or boiling point of pure component 1 and pure component 2.
Yes, sir. Yes, sir.
So positive deviations will lead to minimum boiling azeotrope. Negative deviations will lead to positive or maximum boiling azeotrope. Remember that, ulta hai. And this is the experimental observations. We're not going to theory why it is like that. वो फिर वो molecular interactions देखना पड़ेगा, attraction forces, repulsion force, वो सब देखना पड़ेगा. We are not going there. We are just looking at actually what happens, what kind of behavior we see. Okay, it is not theory. Yeah.
Yes, okay, sir.
We are not talking about theory here. This is not we are not explaining theory. Theory इतना है कि बस positive deviations है, उसका theory पता है हमारे को. Why is it called positive deviations? But why it gives minimum boiling as a drop, then we'll have to look at theory for that, and that is not in our scope. Molecular thermodynamics देखना पड़ेगा हमारे को फिर. ठीक है? So we are not going to get into explanation why it is minimum. It is minimum. For maximum रहेगा तो ये understand कि if it is maximum or if it is positive deviations, it is minimum boiling as a drop. If it is negative deviation, it is maximum boiling as a drop. इतना आपको समझना है. If you want to understand the reason behind it, then we have to go to advanced thermodynamics. ठीक है? यस निरंजन, बोलो.
सर अगर मिक्सचर का कंपोजिशन m से ज्यादा होगा या फिर कम होगा m पॉइंट से, तो फिर क्या होगा सर?
See, क्या होता है ना, when you start distillation, you have to understand distillation क्या होता है. Take a composition of, say, ये लिया मैंने composition. Understand this. I am starting with a liquid which has this composition, right? तो क्या हो जाएगा? I'll get a vapor of this composition. ठीक है? समझ रहे बात?
कुछ दिख नहीं रहा.
कुछ दिख नहीं रहा. I can see it. मैं iPad पे भी चालू कर रखा है, मैंने लैपटॉप पे भी चालू रखा है, so I can see it. If you are not able to see, then it's your network problem. Are others able to see it?
Yeah, sir, it's visible.
Yeah. So दिख नहीं रहा Niranjan, so then it is your network issue because I have two systems now. I have an iPad and I have a laptop. मैं आपको दिखा रहा हूँ iPad पर and I can see that it is visible on laptop also. So I know that there is no network issue here. अगर आपको नहीं दिख रहा then नहीं tell me. सबको नहीं दिख रहा तो बताओ. अगर एक को नहीं दिख रहा then it is 1%.
दिख रहा है सर?
दिख रहा है ना? So most of people are able to see that it is that person's problem. Okay? Because that is very difficult for me to say कि क्या है मेरा इशू है कि नहीं है, इसलिए मैंने दो सिस्टम रखा है. I can see what I am showing in one system in another system.
Okay, sir.
Okay, so if I take this composition 0.3, I'll get a vapor which is composition is 0.6, and what will happen is as distillation proceeds, this composition will go on increasing. Okay, and it will reach a point, this point, where I'll get this liquid which is vapor which is same as liquid composition. उससे ज़्यादा बढ़ेगा ही नहीं because that is a fixed position, fixed composition. उससे ज़्यादा बढ़ेगा ही नहीं liquid composition unless I start with from this point. If I start from this point, then it's a different situation. We're not talking about. We generally have a dilute solution and we want to get a product which has higher composition. Purpose of discussion is that कि मैं अगर 30% methanol water ने start किया, I want to get methanol which is 90%. Objective is that. Okay, and distillation column में multiple stages रहता है, so it goes, you'll see in third year, second semester, or how distillation works. But actually it starts from here. If I take this composition, I'll be able to achieve some composition. अगर अगर azeotrope नहीं बन रहा है, if there is no azeotrope formed, then I have a system like this, and I can start from a feed like this and get a product which has this composition. I can start with 0.2 and I get 0.9.
Okay, sir.
So that's how it works. But when I start with this and in between I have an azeotrope, if I get an azeotrope somewhere here, then it cannot proceed beyond this point. So then I'll get a maximum of 0.7. समझिए बात
Understood,
ये?
sir.
How many
Yes,
people
sir.
understood this point? Raise hands. Only two people understood. Okay, good. So that's why we are looking at azeotrope composition. At the azeotropic composition, the liquid and vapor is same composition. So there's कितना भी उसको boil करेंगे, कितना उसको evaporate करेंगे, vapor is going to have the same composition as the liquid. It's not going to increase. So we'll never get a product which is having composition more than the liquid composition. And then we need to use azeotropic distillation. Or extraction, or different methods. There are other methods of doing it. But by simple distillation, we cannot get anything more than that. And this point is where the curve changes, crosses over, and that is the azeotropic composition. Is this understood?
Yes, sir.
Okay. Similarly for negative, and examples are given here, right? If I look at ethanol water, I can get maximum 89.4% ethanol by distillation. Agar if I start with 10% ethanol in water and I do distillation, big column, maximum I can get is 89.4%. इससे ज़्यादा नहीं मिलेगा मेरे को concentration of ethanol. So if I want 99% ethanol, then I have to use azeotropic distillation. Similarly, other examples. Okay, and जो negative deviations of ideality था उसमें कर्व सिर्फ उल्टा होता है, but concept is same. दिस इज द azeotropic composition, क्रॉसओवर जहाँ होता है y-axis curve का. Again, in this case also I'll get maximum that composition, and examples are chloroform acetone, HCl water, phenol cyclohexanol. मैक्सिमम इतना ही कंपोजिशन मिलेगा मेरे को, उससे ज़्यादा मेरे को नहीं मिलेगा बाय सिंपल डिस्टिलेशन. If I want higher concentration, then I have to resort to other means of doing it, which may be azeotropic distillation, which may be extraction, which may be other things, depending on the system. Is this understood? Before you proceed, this is where we were yesterday.
Yes, sir.
So I want to see hands. How many people understood this? Good. I see sufficient people, so we can proceed now. So now we have to see कि ठीक है ये तो हो गया. Now actually we want to do some calculations. So how do we use this information that at azeotropic composition x is equal to y? We'll use that. Okay. So for that we start using activity coefficients. We have learned activity coefficient is used for what purpose? हमने define किया activity coefficient. Why do we use activity coefficient?
To show the deviation from the ideal one.
Yes. Activity coefficient represents real solutions. So non-ideal solutions, if you are talking about solutions which are non-ideal, then we have to incorporate a factor called activity coefficient, which shows how much is the deviation from ideal solution. So if you plot log gamma versus x, activity coefficient versus x on a log scale. This is log scale, y-axis is log, x-axis is normal. Okay. लॉग स्केल देखा है, लॉग ग्राफ, लॉग नॉर्मल ग्राफ. कभी यूज किया है?
No, sir.
सर देखा है.
देखा है. कभी यूज किया है?
Yes. Yes.
एक मिनट. Okay, so let me show you a log normal graph paper. Can you see this?
Yes, sir.
दिख रहा है? So x-axis is normal, distribution is same, but y-axis में it doesn't start from 0, it starts from 0.1, then it will be 1, then it will be 10, then it will be 100, like that. So this is called log normal. Y-axis is log value, and x-axis is normal value. Normal is 0, 0.1, 0.2, equal distribution. Why is that? Why is it like this? 0.1, 0 से 1 क्यों नहीं है? 0.1 से 1, 1, 10 वगैरह क्यों है? नहीं पता. Nobody knows. कभी यूज किया?
No,
तो या
अच्छा.
Y on y-axis it is 0.1, 1, 10, 1, 0.1, 1, 10 वगैरह. यहाँ 0 क्यों नहीं start होता?
So log of 0 wouldn't exist.
Yes, that is why it is starting from 0.1. So 0.1 से start होता है, 1, 10 वगैरह रहता है. It's always in multiples of 10. And if you see this, it will be, it shows basically represent. If you take log value, log of 1 क्या होता है? What is log
Zero.
of 1?
0.
Log of 10 क्या होता है?
1.
1.
Log of 100 क्या होता है?
10.
2.
2 होता है. So that's why this is uneven scale. That's why the y-axis is uneven and x-axis is even. ये normal scale है, ये log scale है. So what we are talking about is, in this case, we are plotting log because we always calculate equations में जो रहता है log ही रहता है. So we are talking about a log normal graph. Okay. So if you see this, on the y-axis is log normal, log gamma, ln gamma. Equations में हरदम ln gamma आता है, and we plot x with x1. So for ideal solutions like benzene toluene, these are form ideal solution. We'll have gamma equal to 1 for both gamma 1 and gamma 2. Okay. बराबर हमने देखा था, for ideal solution activity coefficient is always equal to 1. Okay. And if you take positive deviations from ideality in this graph paper, again gamma is on the log scale and x1 is a normal scale. So we'll have values above 1 or 1 and above. 1, 2, 3, 4, 5. So these are all positive deviations. Gamma will be always greater than 1 or equal to 1. Equal to 1 कब रहेगा? When it is pure component, right? When x1 equal to 1, this is pure component 1. Right? Pure component के लिए gamma equal to 1 होता है. And when I take x1 equal to 0, this is x2 equal to 1. So it is again pure component. So at these two values, it is going to be 1 for pure component. And for other compositions, the value of gamma is going to be greater than 1. So that is positive deviations from ideality. Is this understood? So positive deviations का दो indication है. One is that partial pressure is greater than that given by Raoult's law, and second is gamma is greater than 1. Is this understood?
Yes, sir.
Okay. So if you take negative deviation of ideality and we plot ln gamma, again gamma on the log scale versus x1 0 to 1, you'll see that at x1 equal to 1, again it is 1, gamma equal to 1 for pure component, and x1 equal to 0, that means x2 equal to 1, again it is 1. Right? And for other compositions, gamma is going to be less than 1. So that is negative deviation from ideality. So remember, when it is positive deviation from ideality, gamma is greater than 1. When it is negative deviation from ideality, gamma is less than 1. Any doubts, questions on this?
सर लेस देन 1 मीन्स नेगेटिव भी होगा क्या?
नेगेटिव नहीं रहता है लॉग स्केल में कभी.
हाँ सर वही.
लॉग स्केल, दैट इज व्हाई इट इज स्टार्टिंग फ्रॉम 0.1. बताया मैंने अभी आपको लॉग स्केल. देयर इज नो नेगेटिव वैल्यू इन log scale. Unless I take minus something, right? It's always something 0 point something. Okay, any doubts, questions? कितने लोग को नहीं समझ में आया ये? कितने लोग को समझ में आया? Raise your hands. Okay, ठीक है. समझ में आया तो अच्छी बात है. Let's move forward then. Now we are going to actually solve some problems using all we have learned so far. So we are going to do calculations for VLE at low pressures first. Okay. So this is all the background for doing these calculations now. So we know Raoult's law is applicable at low pressures, and Raoult's law is YIP is equal to gamma I xi PIS, right? And we will take gamma because we are talking about non-ideal solutions also, not just ideal solutions. Okay, and Gibbs DM equation relates activity coefficient of two components in a binary system given by this equation. So if you take activity coefficient of component 1, if you know the activity coefficient of component 1 and if you know the composition, you can find out activity coefficient of component 2 by this equation. They are related, they are not independent. समझ में आ रही बात? If you take this equation, it relates the activity coefficient of two components. So if one is known, second one can be easily calculated. Just background information. Okay. So now we are going to look at activity coefficient equations because ultimately we want to find out gamma before we actually can use it for calculations. So Margulis equation हमने देखा था पहले, I think few weeks ago, which is ln gamma 1 is equal to ax2 square and ln gamma 2 is equal to ax1 square. One constant, and this equation called is 2 suffix Margulis equation because there are two a and a both they are same. They are mixture. These are applicable to simple systems, molecules which are similar in size, shape, and chemical structure, etc. Other complex के लिए we have to see more advanced or more better equations that are applicable. So this is one equation which you already seen before. Derivation देखा था इसका हमने. And systems are like benzene, cyclohexane, similar systems. We can use it for. How is benzene, cyclohexane similar? Benzene, cyclohexane similar कैसे हो गया? Explain. What is benzene formula?
C6H6.
This is benzene, right? बराबर है?
Yes,
And what is cyclohexane?
C6H12.
Cyclohexane क्या होता है?
C6H12.
C6H12. So cyclohexane is nothing but this. Instead of double bond, there is single bond. That's all. So similar size, similar shape, similar chemical structure. दिख रहा है?
Yes.
So that's why we have to see कि molecules कौन से similar हैं and they are simple to use. Second one is Van Laar equation. Equations are given for gamma 1 and gamma 2. So ln gamma 1 is equal to ax2 square divided by a upon b x1 plus x2 whole square. And ln gamma 2 is given by bx1 square divided by x1 plus b upon a x2 whole square. So there are two constants here. In Margulis we had one, now we have two constants a and b. Okay, and when a is equal to b, if you put a equal to b here, this becomes 1, right? So x1 plus x2 is what? What is x1 plus x2?
One.
X1 plus x2 equal to 1 for a binary system. So denominator becomes 1. So what you get is L1 gamma 1 is equal to ax2 square. Similarly, if a is equal to b, this becomes 1. And what is denominator now?
One.
1. So denominator becomes 1. So it is ln gamma 2 is equal to bx1 square. And if a equal to b, it becomes Margulis equation, right? If a is equal to b, then it is the same equation, right? Margulis equation देखा था हमने. ln gamma 1 is equal to ax2 square and ln gamma 2 is equal to x1 square. So the Van Laar equation reduces to Margulis equation, then a is equal to b. समझ में आया? Van Laar equation, Margulis equation. Any doubts on these two? Okay. So Van Laar equation can be applied to non-polar liquids, benzene, isooctane, propanol, water, etc., etc. Okay. Any doubts, questions on what we have seen, rather Margulis equation and Van Laar equation? How many people understand this? Raise hands. Okay. So now let us see for azeotrophs what happens. For azeotrophs, you know that x1 xi equal to yi or x1 equal to y1. y x2 equal to y2 भी होगा, right? You can use this property of azeotrophs for BLE calculations. Okay. So at Raoult's, if you look at Raoult's law, YIP is equal to gamma I xi PIS. And from here, gamma I is equal to yi into P upon xi PIS. Right? And for azeotroph, xi equal to yi लिया तो gamma I is equal to P upon PIS at azeotropic composition only. हमने देखा वो azeotropic composition is only one composition in the entire 0 to 1 range. So at the azeotropic composition, you can calculate gamma I if you know the total pressure and if you know the vapor pressure of each component. So you can calculate gamma 1 like this and gamma 2 ठीक है. So all you need to know is total pressure of the system and the vapor pressure of each component in a binary system, and we can calculate activity coefficient for that particular component in the system. Is this understood? Yes, Vaibhav, what is the question? Vaibhav, hand raise किया कुछ question
No,
है?
sir.
Okay. So is this understood? How many people understand this now? Raise your hands. Okay, good. So we are going to use this property because it's easier to use and it comes from theory. From theory itself it is coming, it's not simplification or assumption or anything like that. So if you know the vapor pressure, we can calculate vapor pressure from Antoine equation. And if you know the system pressure, we can calculate activity coefficient for each component in the system. And then we can do VLE calculations using this equation. Okay. Anybody has any questions, doubts on what we have done today? Okay, no questions. Then next time we'll solve some examples actually using these concepts which we have developed today. And we'll see how actually we can do VLE calculations.
सर हे टीम्सवर नोट्स अपलोड करता का?
हाँ करता हूँ कल का रह गया था परसों का, कल का आई थिंक परसों तक शायद किया हुआ है
सर।
बट कल का रह गया था, कर दूंगा मैं भी। वीडियोस भी अपलोड किए हुए हैं, एवरीडे शायद नहीं होता है बट ठीक है, वंस अ वीक तो हो ही जाता है। आई ट्राई टू डू अपलोड इट टुडे इटसेल्फ। Murtaza, you have any question?
No, sir.
Okay, so we'll stop here.